Time is something we are all familiar with, yet it remains a profound mystery. In fact, it is a concept so intricately woven into our understanding of the universe, yet so elusive in its true nature, that even the brightest minds have failed to unravel all its secrets. Why does time move forward? This question, seemingly simple at first glance, is anything but. It delves into the heart of our reality, where theories, speculations, and philosophical musings collide in an intricate dance of complexity. The idea that time flows in one direction, forward, has long been a subject of fascination and confusion for both scientists and philosophers. This phenomenon, known as the arrow of time, is more than just a passing notion. It's a deep and enigmatic concept that reaches into the core of how we experience the universe. Time's progression isn't simply the ticking of a clock or the change of seasons. It's a dimension, an essence that binds everything together in an eternal dance of cause and effect. And yet, for all our advancements in science, the real nature of time remains as mysterious as the cosmos itself. In the early 20th century, Albert Einstein's theory of relativity shattered our conventional understanding of time. Before his revelations, time was considered an absolute, a constant that ticked away in the same manner for everyone, everywhere. But Einstein proposed something far more astonishing. Time is relative. It bends and stretches in the presence of gravity, warping under the influence of mass, and at high speeds, it changes altogether. This was no longer a philosophical musing. It was a scientifically observable phenomenon. For instance, astronauts in space experience time differently than those of us on Earth, their clocks ticking at a different rate. This strange and revolutionary idea was proven through experiments like those involving atomic clocks aboard high-speed planes, where time was measured to slow down with increased velocity. It's not just theory, it's a phenomenon we see play out in the real world, one that challenges our understanding of the very fabric of reality. Time, once thought of as a constant, now emerged as something dynamic and interconnected with space. It wasn't just a solitary dimension, it was bound up with the three dimensions of space, forming a four-dimensional framework known as space-time. Time's progression then became part of a larger cosmic puzzle, influenced by the curvature of space itself. Imagine a massive star warping the very fabric of space-time. This is gravity, and it's directly tied to the passage of time. Time moves slower near massive objects like planets or black holes. This effect, though imperceptible in our daily lives, has been measured with such precision that it now has real-world applications, such as in GPS systems, where the slight time difference between satellites and Earth must be accounted for to ensure accuracy. Yet time remains an elusive concept, particularly when viewed through the lens of quantum mechanics. On this scale, time behaves differently. It becomes a backdrop for particles to interact, but it's not a force that bends or stretches like it does in relativity. In the quantum world, time seems to fade into the background, while particles, waves, and forces take the forefront. As scientists continue to probe deeper into the fabric of the universe, they are left grappling with a fundamental question. Can we unite the quantum world with the macroscopic world of relativity? And if we do, what will that reveal about time's true nature? Some theories, like loop quantum gravity, suggest that time is granular, composed of discrete units, like the pixels on a screen, challenging everything we thought we knew about the continuous flow of time. In our everyday lives, we perceive time as a steady, constant force, something we can measure and track with precision. But the deeper we dig, the more we find that this is a highly simplified view. Time, in its true form, is intertwined with space and gravity, stretching, bending, and warping in ways we still don't fully understand. It is the backbone of the universe, the thread that ties everything together, from the birth of stars to the growth of plants to our very existence. Without time, concepts like motion, velocity, and energy would lose their meaning. The unfolding of events, from the rise of civilizations to the aging of stars, all depend on time's unrelenting flow. However, time's role extends far beyond the realms of physics and cosmology. The concept of time has philosophical implications that have fascinated thinkers for centuries. Is time a true, independent dimension of the universe, or is it merely a construct of our human perception? This age-old debate touches on the nature of reality itself, on what it means to exist, and on our place within the cosmos. The way we perceive time has shaped human civilization, from the measurement of days to the creation of calendars, to our deep-seated desire to understand and control it. At the core of time's mystery is the arrow of time, the one-way progression from the past to the future. This concept is not just a theoretical curiosity, it's a fundamental aspect of the physical laws that govern our universe. The second law of thermodynamics, which states that entropy or disorder always increases over time, provides a physical foundation for this arrow. It's why, for example, a cup of hot coffee in a cool room will always cool down. Heat flows from the hot coffee to the surrounding air, and this process is irreversible. It's this relentless march from order to disorder that defines time's flow, and gives us the distinction between past and future. This arrow is not just a feature of everyday life, but a crucial element of cosmology. When the universe was born, it started in a state of extremely low entropy, with order at its peak. Over the billions of years since the Big Bang, time has driven the universe toward higher entropy, a state of greater disorder. The distinction between the past and the future is shaped by this inexorable increase in entropy. As time moves forward, the universe becomes more complex, and the order we observe in the cosmos gives way to greater randomness. But time's flow is not as simple as it seems. In quantum mechanics, time is not necessarily bound by a one-way direction. The laws of quantum mechanics are time-symmetric, meaning they don't change whether time flows forward or backward. This creates a striking contradiction. At the microscopic scale, time doesn't seem to have a preferred direction. Yet at the macroscopic scale, the arrow of time is unmistakable. How do we reconcile this discrepancy? It's one of the greatest challenges in modern physics. As we probe deeper into the nature of time, we are confronted with questions that have no easy answers. Why does time move forward? And what does this say about the nature of reality itself? Is time a fundamental dimension of the universe, or a mere illusion shaped by our perceptions? These are questions that remain unresolved, mysteries that continue to elude even the most advanced minds. And as we look to the future, one thing is clear: time will continue to be one of the greatest enigmas we face, a riddle whose solution could unlock the deepest secrets of the universe. However, there is more to the story than meets the eye. Einstein's theory of relativity opened a door to a radically different understanding of time, one that suggested time might not be the constant and unyielding flow we once believed it to be. In the presence of strong gravitational fields, or at speeds approaching that of light, time could stretch, bend, and even slow down. In essence, time was not an immutable river rushing forward. It could be altered depending on where you were and how fast you were moving. Yet, despite these intriguing properties, relativity did not disrupt the idea of time's one-way progression. It merely redefined how we perceive its passage. Still, the true enigma of time's flow surfaces in the strange, mysterious world of quantum mechanics. At the scale of atoms and subatomic particles, where classical physics loses its grip, time's flow becomes disturbingly ambiguous. Here, the fundamental laws of particle interactions governed by quantum mechanics are largely time-symmetric. This means that the equations describing these interactions remain valid, whether time is moving forward or backward. In other words, at the microscopic level, time doesn't have a preferred direction. Unlike the macroscopic world, where entropy increases and objects age, thus reinforcing the arrow of time, the quantum world operates on a different set of rules. The symmetry of time in quantum mechanics presents a paradox, one that defies our everyday understanding of how time should behave. This contradiction presents a profound challenge for physicists trying to reconcile the laws of thermodynamics with the strange, time-symmetric nature of quantum theory. Is the forward movement of time a universal truth, or does it depend on the scale at which we observe the universe? The macroscopic world we experience offers a clear answer. Time flows forward, as evidenced by the inevitable increase in disorder and the aging of living things. But when we zoom into the quantum level, the directionality of time becomes far less certain. Could time, in theory, flow backward in the microscopic world? The answer isn't so simple, and bridging this gap between the two realms remains one of the most perplexing challenges in modern physics. As our understanding of the universe deepens, so too does the realization that time, in its most fundamental sense, is not the simple, steady flow we once assumed. Rather, it is a malleable concept shaped by gravity, velocity, and the unseen forces at work beneath the surface of reality. This is where Einstein's theory of relativity reveals its true complexity, challenging our perception of time's constancy. According to this groundbreaking theory, time itself is not absolute. It can stretch or contract based on the gravitational pull of nearby objects or the speed of motion. In extreme environments, such as near a black hole, the fabric of space-time itself becomes distorted. Time slows down dramatically under the influence of a massive object's gravity. This phenomenon, known as gravitational time dilation, means that the closer you are to a massive body, the slower time will seem to move. The starkest example of this occurs around black holes, where gravity is so intense that it warps space and time in ways that seem almost impossible. Time moves at a different rate near these behemoths of the universe, and this dilation becomes more pronounced the stronger the gravitational field. Velocity, too, plays a critical role in how we experience time. According to Einstein's special theory of relativity, the faster an object moves, the slower time passes for it relative to someone at rest. While this effect is imperceptible at the speeds we experience daily, it becomes significant as an object approaches the speed of light. Imagine astronauts on a spacecraft traveling at near light speeds. From their perspective, time would slow down, and they would age more slowly than people on Earth. This time dilation due to velocity has been experimentally confirmed by measuring the decay rates of particles moving at high speeds and by comparing clocks on high-speed aircraft to those on the ground. These experiments demonstrate that time, as we perceive it, is not a constant, unchanging flow, but rather a variable that can be influenced by factors like gravity and speed. But what about the idea of time moving backward? At first glance, this seems like a concept ripped straight out of science fiction. In our daily lives, time only ever moves forward. There is no going back. But in the mysterious world of quantum mechanics, this assumption begins to unravel. While classical physics tells us that time moves in one direction, quantum mechanics offers a more puzzling picture. Many of the equations governing quantum interactions are time-symmetric, suggesting that, at least at the subatomic level, time could theoretically move in either direction. This raises the tantalizing possibility that time at its most fundamental level may not be so unidirectional after all. Yet, this quantum ambiguity does not mean that we'll soon witness time-reversed events in our everyday lives. The laws of thermodynamics, which govern the macroscopic world, ensure that processes like the cooling of a hot object or the breaking of a glass are irreversible. The second law of thermodynamics states that entropy, or disorder, will always increase over time, reinforcing the forward flow of time in the visible world around us. So, while quantum mechanics offers a tantalizing hint that time might, in theory, be reversible, the larger picture remains one where time moves in one direction, toward greater disorder and decay. The idea of time reversal doesn't just challenge our understanding of physics. It raises profound questions about causality, the very structure of cause and effect. If time could move backward, the fundamental principles that govern our universe would be upended. The order in which events unfold, where causes precede effects, could be completely reversed. This is not just a philosophical conundrum, but a physical one, with far-reaching implications for our understanding of everything from the birth of the universe to the fate of its eventual end. The question of whether time can ever move backward may remain unanswered, but the mystery it presents will undoubtedly continue to captivate and challenge scientists for years to come. But also, our very conception of reality, what we perceive as time, our experiences, and our understanding of existence, may not be as fixed and absolute as we once thought. What if time, the very thing we rely on to measure our lives, moves in ways we cannot fully comprehend? There are theories, many of them rooted in physics and cosmology, that attempt to explain why time moves forward, unraveling not just the mechanics of the universe, but also the mysteries that lie beyond human perception. One of the most widely discussed theories is rooted in the second law of thermodynamics. In simple terms, this law states that entropy, the measure of disorder or randomness, tends to increase over time in an isolated system. Imagine a once ordered stack of blocks or the smooth surface of a pond. Over time, blocks topple, water ripples, and the system moves from a state of neat order to one of chaotic disorder. The universe in all its complexity follows this same trajectory. The hotter coffee cools, buildings decay, and energy disperses. This increasing entropy gives direction to time, marking its irreversible flow from past to future. In this framework, time is always flowing forward, driven by the statistical likelihood that disorder will increase. It's an idea so deeply ingrained in our understanding of reality that it seems almost impossible to think of time moving in reverse. But what if time could bend? What if there were ways that time could behave differently, even in tiny, almost imperceptible shifts? Another theory comes from the very birth of the universe itself, the Big Bang. According to this theory, time, as we know it, began in a state of extreme low entropy. The universe was dense and hot, with all the matter and energy packed into an infinitesimally small space. But as the universe began to expand, entropy started to rise, defining the direction of time. What makes this concept so intriguing, though, is not just how time started, but why it began in such a state of low entropy. Why, after such an unimaginable event, did time seem to spiral forward in a way that leads us to the universe we now inhabit? Yet, even in this seemingly straightforward narrative, there's another layer to consider: quantum mechanics. At the quantum level, time itself can appear symmetrical, meaning it doesn't always show a clear direction of flow. This is puzzling. If the universe is governed by laws that don't inherently favor one direction, then why do we experience time so differently at the macroscopic level? Could the act of measurement, the moment when we observe and define a quantum system, be the very thing that sets time into motion, making it one way? In a sense, when we measure, we collapse the possibilities of the quantum world into a single moment, a snapshot of reality that gives rise to the perception of time flowing forward. There is yet another theory, one that is tied to the ongoing expansion of the universe itself. As the universe stretches outward, its internal order disintegrates, leading to greater and greater entropy. In this theory, the expansion of space is directly tied to the arrow of time. As the universe expands, time ticks forward inexorably, following the increasing disorder. Yet, this idea also introduces a fascinating possibility. If the universe were to ever begin contracting, could it reverse the flow of time? This is, of course, a hypothetical scenario, one that doesn't align with our current understanding of cosmology, but it raises a thought-provoking question about the nature of time itself. The relationship between entropy and time has profound implications, not just in understanding the universe, but in how we perceive the passage of time. The second law of thermodynamics gives us a simple yet profound understanding. Time flows in one direction because entropy increases. Consider a box filled with two gases, each contained on opposite sides. When released, the gases will naturally mix, moving from a state of low entropy order to high entropy disorder. Once the gases have mixed, it's highly unlikely, though not impossible, that they would spontaneously separate again. This one-way progression from order to disorder mirrors how we experience time moving from past to future, a direction that is irreversible in our everyday world. But what about the realm of quantum mechanics? Here, things become much more complicated. At the quantum level, the laws of physics do not prefer one direction of time over another. The fundamental actions at this scale are symmetric. Time flows in both directions equally. However, this symmetry doesn't explain the clear arrow of time we experience in the macroscopic world. This is where the concept of time dilation, a fascinating aspect of Einstein's theories of relativity, offers us a new lens through which to examine time. According to Einstein's general theory of relativity, time is not constant. It bends and stretches in response to gravity. In places with stronger gravitational fields, like near a massive star or black hole, time moves more slowly. This phenomenon, known as gravitational time dilation, means that clocks at the surface of Earth tick more slowly than those in high-altitude satellites. In the context of everyday life, this effect is minimal, but in the precision of GPS technology, it must be accounted for. But what happens when we move at speeds close to the speed of light? According to special relativity, time dilates even further, slowing down for objects moving at such high velocities compared to those at rest. This concept, often referred to as relativistic time dilation, has been confirmed by experiments involving fast-moving particles and atomic clocks on moving aircraft. For those traveling near light speed, time itself behaves differently, further challenging our understanding of the steady flow we once thought to be immutable. And then there are black holes, mysterious cosmic phenomena that warp space and time in extreme ways. The intense gravitational pull near a black hole bends time so dramatically that at the event horizon, time as we know it slows to a crawl. Nothing can escape once it crosses this boundary, not even light, marking the point at which the flow of time itself is altered beyond recognition. As we peer into the black hole's depths, we are forced to question what we know about time, reality, and the very fabric of the universe itself. All of this, time's forward motion, its bending and warping, its increase in entropy, its mysterious relationship with the birth of the universe, suggests that time is not the absolute fixed quantity we once believed it to be. Instead, it is a dynamic, flexible force, influenced by gravity, motion, and the very laws of physics that govern our existence. The mysteries of time are far from solved, but they offer us a glimpse into a universe far stranger and more wondrous than we could ever have imagined. The gravitational pull near a black hole is so powerful, it bends time in ways we can hardly comprehend. As the immense mass of a black hole warps the fabric of space-time, it significantly slows down time for anyone near it compared to an observer far away. This phenomenon, known as gravitational time dilation, is one of the most intriguing predictions of Einstein's theory of general relativity. As a black hole's gravitational pull intensifies, time behaves differently. Imagine standing next to a clock near a black hole. From a distant observer's perspective, the clock would appear to tick slower and slower, eventually seeming to freeze as it nears the event horizon, the point of no return. But what does this really mean? It suggests that time, something we take for granted, is not the same everywhere in the universe. Near a black hole, time dilates, becoming almost still, while far away it flows normally. For instance, an astronaut orbiting a black hole would experience only a few moments passing by, while years might pass for those back on Earth. This isn't just a thought experiment, it's a practical demonstration of how gravity can manipulate time in ways we rarely see on our planet. But it doesn't stop there. The nature of time in black holes hints at even stranger ideas, ones that challenge the core of physics. Some theories propose that the intense gravitational forces near a black hole might stretch space-time so much that they create tunnels or wormholes that connect distant points in space and time. Wormholes remain a speculative concept for now, largely theoretical and often debated. But the very idea opens the door to countless possibilities. Could they allow us to travel instantaneously across vast stretches of the universe? Could time itself become a more malleable entity? Moreover, black holes raise profound questions about the nature of information and matter. What happens to them when they fall into a black hole? Does information vanish, or is it preserved in some way? This leads to the notorious information paradox, which has kept physicists awake at night. If information were truly lost in black holes, it would challenge the conservation laws that govern physics, particularly the principle of information conservation. This paradox, while not yet resolved, suggests that our understanding of time, causality, and the fundamental workings of the universe may still be incomplete. As we venture further into the unknown, we begin to question the very direction of time. We usually think of time as an arrow, moving from past to present to future. But is this always the case? Theories about time's arrow, grounded in thermodynamics and quantum mechanics, suggest that time doesn't always flow in one direction. In fact, experiments with subatomic particles, those that interact through quantum mechanics, show that at the most fundamental level, time appears symmetric. Whether time flows forward or backward, the fundamental interactions don't change. This symmetry clashes with our everyday experience, where events unfold in a definite order. Does this mean time's flow is an illusion or merely an effect of the way we perceive it? Research into closed systems, like those involving entropy, further complicates the issue. Entropy is the measure of disorder, and in isolated systems, it naturally increases over time, giving us our sense of time's arrow. Experiments that measure entropy in gases, for example, consistently show that it grows as time passes, reinforcing the idea that time points in one direction. from past to future. However, does this mean the future is predestined, or could there be a way to reverse the process? The cosmic scale provides further insights. Astronomical observations, like the study of the cosmic microwave background radiation and the expanding universe, reveal that the universe itself has been evolving over time, from a highly ordered state at the Big Bang to the increasingly disordered present. This supports the notion that time is directional, rooted in the evolution of the cosmos. But what if the universe, in some distant future, undergoes a reversal or cycles back to its original state? This question remains in the realm of speculation, but it tantalizes physicists with its complexity. Further theorists have proposed experiments to test whether closed time-like curves, paths in space and time that loop back on themselves, could be physically realized. Such experiments, grounded in the strange nature of general relativity, might someday reveal new dimensions to time itself, perhaps even making the impossible possible. But until we break the boundaries of our current technology, such tests remain theoretical, exploring the edges of what we understand. As we delve into the peculiarities of quantum mechanics, we find that it complicates even our most fundamental assumptions about time. In quantum theory, particles can exist in superposition, meaning they can occupy multiple states simultaneously until they are measured. This introduces a paradox. The state of a system is undefined until observed, which muddles our understanding of how time unfolds. One of the most famous examples of this is Schrödinger's cat thought experiment, in which a cat is both alive and dead until the box is opened. Could time itself be in a superposition, not a simple linear progression, but a set of possibilities that collapse into reality only when observed? Quantum entanglement adds yet another layer to this mystery. When particles become entangled, the state of one particle directly influences the state of another, even across vast distances. This instantaneous connection seems to defy our conventional understanding of time, where information should travel at finite speeds. Could this suggest that time, in certain contexts, might not be as absolute as we think? Perhaps most perplexing of all is the concept that, in some interpretations of quantum mechanics, time may not even exist as a fundamental dimension. Models such as the Wheeler-DeWitt equation propose that time emerges only under specific conditions, potentially rendering it not a backdrop of the universe, but a byproduct of physical processes. Now, as we step into the more speculative realms of physics, we encounter the theory of wormholes. These hypothetical structures, once considered purely fictional, have become a key subject of scientific inquiry. In simple terms, wormholes act as shortcuts through the fabric of space-time, connecting distant points in space in an instant. If they exist, they could allow for travel between different points in the universe, or perhaps even between different times. But could they also be portals to alternate realities or universes? Though the concept originates from Einstein's equations, wormholes are still theoretical. These potential bridges in space-time may one day offer answers to questions we have yet to fully grasp about the very nature of time, space, and gravity. For now, wormholes remain as mysterious as the black holes themselves, fascinating ideas that push the limits of our imagination and understanding of the cosmos. However, it's important to note that these theories, while compelling, remain speculative. Their presence in scientific discussions is based largely on mathematical formulations and not on actual empirical evidence. Despite this, wormholes remain an intensely intriguing possibility. If they do exist, wormholes might offer a passageway not only between two distant points in space, but also across time itself. This is a direct consequence of Einstein's theory of relativity, which allows for the curvature of space-time in such a way that it could potentially link separate time points. But this theoretical framework raises more questions than answers. In this mysterious scenario, the idea of traveling through a wormhole might seem almost magical. The thought of traversing through the fabric of space and time to witness moments from the past or glimpse into the future stirs the imagination. Yet, the challenges are immense. First, there is the enigma of exotic matter, a theoretical substance with negative energy density and negative pressure, which is required to stabilize a wormhole. Such matter has yet to be observed in the form necessary for maintaining a traversable wormhole. Without it, the wormhole would collapse, leaving no opportunity for travel, rendering it a mere fantasy rather than a scientific reality. Additionally, time travel introduces paradoxes that challenge our understanding of causality. The grandfather paradox is perhaps the most famous example. If a time traveler were to go back and alter the past, they could potentially prevent their own existence. These paradoxes force us to question whether the universe allows such alterations or whether time itself holds unbreakable laws. Can the past truly be changed, or is everything set in an unalterable stream? The very idea of time travel defies our current understanding of physics, causing more confusion than clarity. Theoretical time travel is based largely on the principles of general relativity. Yet time dilation, the warping of time caused by the immense gravity of objects like black holes, offers an intriguing glimpse into how time could behave in extreme conditions. When an object moves near a massive body, like a black hole, time for that object slows down relative to others far away from the gravitational field. This isn't time travel in the science fiction sense, but it does suggest that time is not as absolute as we once thought. Time can pass at different rates depending on one's position in the universe, which raises questions about the true nature of time itself. Beyond wormholes and black holes, time travel theory also touches on the possibility of traveling to the future, which seems more achievable, though still far beyond our current capabilities. If a person could move at speeds approaching the speed of light, time for them would pass slower compared to those at rest, effectively enabling them to experience the future while the world around them moves ahead. This might seem like an easier route to time travel, but it's hindered by insurmountable technological barriers, such as achieving those relativistic speeds. The future might be within reach, but the technology to get there seems like a distant dream. Yet, traveling to the past remains a far more elusive and paradoxical challenge. The mere concept of backward time travel presents numerous issues in terms of both physics and philosophy. The grandfather paradox encapsulates this dilemma, suggesting that if backward time travel were possible, the very structure of cause and effect could unravel. The laws of physics, most physicists agree, are likely designed to prevent such time travel from ever occurring, to preserve the integrity of causality and avoid logical contradictions. Now, turning to the more cosmic scale of time, there's the question of the end of time itself. According to cosmology, the universe is gradually expanding, and in the distant future, this expansion will result in the universe growing colder and darker, a process known as the Big Freeze. In this scenario, the energy that powers stars will be exhausted, galaxies will drift further apart, and the universe will approach absolute zero, the theoretical temperature at which no thermal motion exists. This isn't an immediate concern, but rather an eventual fate that will unfold over trillions of years. It's a haunting vision of a future where not only stars, but all forms of life and movement fade into nothingness. This is where the concept of heat death comes in, where entropy reaches its maximum and the universe reaches thermodynamic equilibrium. In this state, no energy would be left to perform any kind of work or change. All processes would cease, and everything in the universe would become a uniform, static void. There would be no variation in temperature or energy gradients, nothing to propel the dynamic processes that govern our world. It would be the ultimate stillness, a chilling prospect for those who look to the future. However, there's a more dramatic and violent end proposed by the Big Rip theory. Here, dark energy, the mysterious force accelerating the universe's expansion, could grow stronger over time, pulling apart not only galaxies, but even atoms. This scenario imagines a universe where the fabric of space itself tears apart, stretching until nothing remains but infinite separation. Whether the universe ends in the slow collapse of stars and warmth or the violent ripping apart of everything, both scenarios leave us contemplating a universe far removed from the vibrant existence we experience today. Philosophically, these theories push us to question the very nature of time and existence. Are we living in a cosmos bound by time, or is it all an illusion? Could time itself, as we perceive it, be nothing more than a fleeting human construct, or is it a fundamental force that governs all things? Time remains one of the greatest mysteries, both in science and in thought. The complex interplay of space, time, and gravity continues to puzzle even the greatest minds. As we delve into the nature of time through the lens of both relativity and quantum mechanics, we encounter deeply conflicting views. While relativity treats time as a malleable entity, quantum mechanics insists that time is fixed, a backdrop for the unpredictable behavior of subatomic particles. This dichotomy, often referred to as the problem of time, remains one of the most significant barriers in unifying the two theories into a comprehensive framework of quantum gravity. Moreover, our subjective experience of time adds an additional layer of complexity. Time flows continuously in our consciousness, but whether this perception matches the true nature of time, or if it is simply a construction of the mind, is an enduring question in both physics and philosophy. A fascinating theory that attempts to reconcile these discrepancies is the block universe theory, a model where time is treated as a static dimension. According to this view, past, present, and future all exist simultaneously within a vast four-dimensional block. The flow of time, as we experience it, is merely an illusion. What we perceive as the future already exists within this block, unchangeable and fixed. This theory not only challenges our understanding of causality and free will, but also presents time as something far more complex than we've ever imagined. Under this model, the universe isn't a fluid, dynamic process, but a vast static structure, with all moments existing side by side. It raises profound questions about the nature of existence and whether the future is set in stone, or if our choices truly matter in the grand scheme of things. Is the universe truly deterministic, or do we possess the freedom to alter the course of events? These questions challenge our perception of time and the role we play within it. In essence, the block universe theory reshapes our understanding of time, offering a vision of a universe that is more than just a linear progression from past to future. It suggests that time, like space, is a dimension, an aspect of reality that is not bound by the flow we experience. As time dilation, as predicted by relativity, continues to shape our understanding of the universe, we are left to wonder, how much of time as we know it is truly as we perceive it? In the block universe model, the perception of time, though varying, is merely different paths through the vast expanse of four-dimensional space-time. This concept neatly aligns with experimental evidence supporting time dilation, like the variations in time recorded by atomic clocks both on Earth and in satellites orbiting far above. However, as convincing as this theory may seem, it has its fair share of critics. Detractors argue that it conflicts with the inherent randomness found in quantum mechanics, the branch of physics that governs the behavior of subatomic particles. Quantum mechanics introduces an element of uncertainty in the behavior of particles, a feature that seems incompatible with the deterministic nature of a predetermined block universe. Could it be that the universe, at its very core, operates without time? This question beckons exploration. Time traditionally is viewed as a measure of change, a framework within which we comprehend the unfolding of events. In classical physics, time is often depicted as a continuous, forward-moving river, carrying us from one moment to the next. This aligns with our everyday experiences, where cause and effect follow in a linear progression. But when we delve into the realms of advanced physics, the nature of time transforms into something much more elusive and multifaceted. According to Einstein's theory of general relativity, time is not separate from the three dimensions of space. Instead, they form a unified, four-dimensional fabric known as space-time. This fabric is warped and curved by the presence of mass and energy. In this sense, time is not just a passive backdrop against which events unfold, it's an active participant in the dynamics of the universe. For instance, the second law of thermodynamics, which states that entropy, or disorder, increases over time in an isolated system, is fundamental to our understanding of physical processes. Without time, this principle would lose all meaning. Time provides the context necessary for us to understand the progression of events, and without it, concepts like causality, the relationship between cause and effect, would vanish, rendering the entire structure of existence meaningless. Without time, change itself becomes an impossibility. It is a fundamental, irreplaceable feature of the universe, allowing us to measure and understand the progression of the cosmos. Yet we must ask ourselves, is time truly a measurable unit, or is it just a concept we've imposed upon the universe to make sense of it? This brings us to one of the most intriguing questions in the field of cosmology. What is the smallest measurable unit of time? This topic fascinates those at the cutting edge of science and philosophy. The answer lies in a concept known as Planck time, named after the German physicist Max Planck, who is considered the father of quantum theory. Planck time is an extraordinarily brief duration, approximately 5.39 by 10 by 44 seconds. To put this into perspective, it is so brief that even light, the fastest thing in the universe, would travel only a fraction of the diameter of a proton in this minuscule period. This concept emerges from the Planck scale, a domain of physics where the effects of both quantum mechanics and general relativity become intertwined and significant. At the Planck scale, our conventional understanding of physics begins to crumble. Here, the classical descriptions of gravity and spacetime are no longer valid. The fabric of spacetime itself is believed to be quantized, composed of discrete, indivisible units, akin to the pixels on a digital screen. Planck time is derived from fundamental constants in physics, such as the gravitational constant g, which appears in Newton's law of gravitation, the speed of light c, and Planck's constant, h, which governs quantum mechanics. These constants are woven together in a mathematical formula that defines the Planck time, representing a theoretical limit to how finely we can measure time. However, while Planck time is a fascinating theoretical concept, it remains beyond our current capacity for measurement. Even with the most advanced atomic clocks, we can only measure changes in time down to the scale of attoseconds, 10 to 18 seconds. Still many orders of magnitude longer than Planck time. Despite this, the implications of Planck time stretch our understanding of the universe to its limits, pushing us to reconsider the very nature of time itself. As we ponder this unfathomably small unit of time, we are compelled to question how fundamental particles, the building blocks of reality, interact with time at the most minute levels. At the subatomic scale, the behavior of fundamental particles like quarks and leptons, including electrons and neutrinos, defies our everyday understanding of how objects should behave. In the strange world of quantum mechanics, particles do not experience time in the linear, in humblest caught, straightforward manner that we do. Instead, their behavior is governed by probabilities and uncertainties. One of the core principles of quantum mechanics, known as the Heisenberg uncertainty principle, asserts that certain pairs of physical properties, such as position and momentum, cannot be precisely measured at the same time. In a similar vein, there exists a fundamental relationship between energy and time, a relationship that remains a subject of much mystery and debate. As we venture further into these questions, it becomes clear that our understanding of time is far from complete. Whether we look at the intricacies of Planck time, the interplay between quantum mechanics and general relativity, or the fundamental randomness that governs the smallest particles of the universe, time remains one of the most profound and elusive dimensions of reality. And as science progresses, we may find ourselves at the precipice of a new understanding of time, one that may fundamentally alter the way we view the very fabric of the universe itself. And so, when we look at the smallest units of time, approaching the Planck scale, we are confronted with a fascinating revelation. There's a fundamental limit to the precision with which we can measure the energy of particles. This uncertainty, stemming from the very nature of time and space, is what leads to the brief and seemingly paradoxical phenomenon of particle-antiparticle pairs spontaneously appearing from the vacuum of space. These pairs, known as virtual particles, emerge only for incredibly brief moments, in perfect accordance with Heisenberg's uncertainty principle. But their existence, though fleeting, is nothing short of mysterious. These particles momentarily dance in and out of existence, revealing just how little we truly know about the deepest workings of our universe. As we venture deeper into the realm of particle physics, we are introduced to a more cryptic idea, time reversal symmetry, or T-symmetry. In certain conditions, the equations that govern particle behavior appear to hold true whether time is flowing forward or backward. This suggests that at the fundamental level, the laws of physics might not care whether time is moving forward or backward. Yet, as we step back into the macroscopic world, this symmetry seems to fade away. We don't see objects moving backward in time. We don't observe time reversing itself. This is where the second law of thermodynamics takes center stage. It tells us that entropy, a measure of disorder, always increases over time. In simple terms, this gives time its arrow, pointing from a state of lesser disorder to greater disorder. This is where things get truly intriguing. The notion that the universe may not favor a particular direction of time is a concept that challenges the very core of our human experience. This brings us back to the grand question of why time moves forward at all. Could it all just be an illusion? This question, seemingly philosophical, cuts to the heart of modern physics and cosmology. The arrow of time, with its undeniable directionality, governs much of our existence. We remember the past, but not the future. We age, we grow, but we never reverse these processes. It's a one-way street, and we all travel on it without exception. Yet, could this experience of time be nothing more than a product of our consciousness? Could our brains, in processing the flow of events, be creating an illusion of a forward-moving time? In classical physics, time is often treated as a constant, a river that flows endlessly from past to present to future. But as we step into the quantum world, this view begins to unravel. The laws governing subatomic particles don't inherently distinguish between past and future. Could this mean that the forward flow of time as we experience it is merely a construction of our minds, rather than a true property of the universe itself? And this is where things take a turn for the even more strange. The second law of thermodynamics, which posits that entropy increases over time, also leads us to believe that time moves in one direction. As systems evolve, they tend toward greater disorder, creating a natural sense of progression. But does this mean that time is an irreversible march forward? Or is it simply that our perceptions are locked into this direction, shaped by the entropy we observe around us? The mysteries only deepen as we explore these questions further, looking for answers not just in the equations of physics, but in the very fabric of reality itself. In the realm of speculative ideas, some have even ventured to suggest that time may have flowed backward before the Big Bang, offering an entirely new perspective on the very beginning of the universe. These theories are wild, unproven, and still highly controversial, but they offer a tantalizing glimpse into what might be possible when we push the boundaries of our understanding. The more we explore the implications of time symmetry and the potential for time to reverse, the more we realize that our perception of time is not just a simple flow from past to future, but a profound mystery that challenges the deepest concepts of physics, philosophy, and the very nature of reality itself. But it doesn't necessarily mean that time itself has a direction. Some theorists have proposed that the universe, at its most basic level, might be time symmetric, with no preferential direction. In such a scenario, the forward movement of time that we experience could be more of an emergent phenomenon, arising from the laws of thermodynamics and the initial conditions of the universe, rather than from the very fabric of time itself. Imagine a cosmic stage where time, instead of being a flowing river, is a stagnant pool, where our perception of progression is merely an illusion constructed by the interplay of cosmic forces. Building on our exploration of whether the forward movement of time is an illusion, we naturally segue into the fascinating and mysterious relationship between consciousness and time perception. This intersection lies at the very heart of a grand puzzle where science and philosophy intertwine in ways that leave us questioning the very nature of our existence. Consciousness, the state of being aware and able to think about one's own existence, has a profound influence on how we perceive time. In fact, our subjective experience of time can vary dramatically from the objective tick-tock of clocks and calendars. Have you ever noticed how time seems to fly when you are engrossed in a captivating task, yet drags on interminably when boredom takes hold? This paradox reveals that our perception of time is not a fixed, linear path, but is instead malleable, stretching and compressing depending on our mental state and engagement. Neuroscience, as it ventures deeper into the labyrinth of the mind, has begun to uncover some of the mysteries behind this phenomenon. Researchers have found that different areas of the brain are involved in processing time, and our perception of time can be influenced by a multitude of factors. Attention, memory, emotions, and even neurological disorders can alter how we experience the passage of time. For instance, when we are fully immersed in a task, our brains process more information within each passing second, creating the sensation that time is slowing down. The relativity of time perception becomes even more striking in life-threatening situations. Many individuals have reported experiencing events in slow motion during moments of danger. This could be due to the brain shifting into a high alert mode, processing information at an accelerated rate to help us react swiftly. However, intriguing studies suggest that this perception of slowed time may not be an accurate reflection of what was happening in the moment, but rather how we remember it. During these intense moments, our brains record an abundance of sensory details, creating the illusion of a prolonged experience when we reflect on it. Philosophically, the link between consciousness and time perception opens a Pandora's box of profound questions about the nature of reality. If our perception of time can be so easily influenced by our mental state, how much of the passage of time is truly an objective feature of the universe, and how much is a mere construct of human consciousness? Is time a universal constant, or is it shaped by the very minds that experience it? This question leads us seamlessly into the role of memory in shaping our perception of time, drawing us deeper into the enigma of human consciousness. Memory, an integral facet of our awareness, holds the key to understanding how we experience time. Memory allows us to store and recall past experiences, effectively creating a personal timeline of our lives. This mental timeline is essential to our understanding of time. It is through memory that we come to grasp the passage of days, months, and years, and our recollections play a crucial role in how much time we feel has passed. For example, recall a time when you were on vacation or learning something new, and it seemed as if time stretched infinitely. In contrast, a period filled with repetitive or mundane activities might seem to pass by in the blink of an eye. This effect, known as the holiday paradox, reveals that the richness of our experiences, not the actual duration, shapes our perception of time. When we look back on a period filled with novelty and excitement, it often feels longer because the density of memories has expanded our mental timeline. This phenomenon is not just about the quantity of memories, but the emotional charge they carry. Emotional events, whether joyful, traumatic, or sorrowful, are often vividly etched into our memories, making them feel as though they lasted longer. Time often feels like it's dragging during difficult or painful moments, while it seems to race by when we are basking in happiness. Moreover, as we age, the way we perceive time shifts. The process of creating new memories tends to slow down, causing time to feel like it speeds up as we grow older. This effect explains why childhood and early adulthood often seem to last longer. These periods of life are packed with new experiences, firsts, and dramatic changes, all of which create a rich tapestry of memories that stretch time. Further complicating this mystery, the way we recall memories is not always linear. We often recall events out of sequence, and our perception of time can be influenced by how frequently we revisit certain memories. The more often we think about an event, the more significant and extended it may seem in the context of our mental timeline. In a way, we can reshape our sense of time through the act of remembering, as though we are rewriting the very fabric of our past. And much like humans, animals too experience time, though their perception may differ in ways that we are only beginning to understand. But their perception of time can be markedly different, influenced by various factors, including their size, metabolic rate, and ecological needs. Picture a small, rapid creature darting around its environment. The perception of time to it is radically altered. For instance, smaller animals with faster metabolic rates like birds and insects experience time in finer slices. This allows them to process visual information more rapidly, reacting to their surroundings with incredible speed. A prime example is the common fly, whose reflexes seem almost superhuman compared to humans. It can detect and respond to movement in a fraction of the time we can, almost as if it exists in a different temporal reality. Studies reveal that this difference in how time is perceived is deeply connected to the animal's nervous system. The speed at which the nervous system processes incoming stimuli plays a critical role in shaping how an organism experiences time. For animals like birds and insects, whose survival depends on quick reactions, whether to escape predators or snatch fast-moving prey, time seems to stretch out in a way that gives them a crucial edge. It's almost as if they exist in a world where seconds feel like minutes, offering them an advantage in a life-or-death race against the clock. Moreover, the lifespan of an animal also colors its perception of time. Take, for example, a mouse. A single year constitutes a significant chunk of its life, while for humans, it's but a small fraction. For creatures with short lifespans, a brief moment could seem like an eternity, magnifying the significance of every fleeting second. Time, for them, isn't just something that passes, it's something that shapes their very experience of the world around them. Interestingly, the time perception of certain species even influences their behavioral strategies. Migratory birds, for instance, follow seasonal patterns governed by subtle changes in daylight, displaying an awareness of time's longer cycles. The passage of seasons isn't just a phenomenon they sense, it's a cue that drives critical decisions for survival. But what if animals, like squirrels, are aware of time in a way that extends beyond the present? Consider how squirrels hoard food for the winter. Their actions imply an understanding of future needs, a foresight into time that's essential for survival. Some primates have been observed crafting tools and planning for later use, behaviors suggesting a mental representation of future events. However, it remains unclear whether this future thinking is a conscious grasp of time in the human sense, or simply an instinctive reaction to environmental cues. This fascinating link between time perception and survival behaviors invites us to explore how time not only shapes an animal's actions, but also its very existence. As we dive deeper into time's influence on life, we reach a complex intersection of biology, physics, and philosophy. Aging, the inevitable process that all living organisms undergo, is intrinsically tied to time itself. The passage of time is not just an abstract concept. It is etched into the very fabric of biological systems. Over time, cells accumulate damage from environmental factors, genetic influences, and the natural limits of cellular replication. This cellular decline, this inexorable march towards senescence, is what we experience as aging. The aging process in its most raw form is the relentless accumulation of time's toll on the body. Interestingly, the rate at which an organism ages can vary drastically depending on several factors. Smaller animals like mice with faster metabolisms tend to have shorter lifespans, while larger animals like elephants enjoy slower metabolisms and longer lifespans. This relationship has birthed the rate of living theory, suggesting a direct link between metabolism and lifespan. Yet this theory doesn't fully explain why some species, such as certain tortoises, can live far longer than their metabolic rate would suggest. There's something more to the story of time and aging than just metabolism. At the cellular level, the concept of telomeres, protective caps at the ends of chromosomes, plays a pivotal role. With each cell division, these telomeres shorten, and once they reach a critically short length, cells stop dividing and become senescent, a key factor in aging. Yet some species, like lobsters, possess the enzyme telomerase, which allows them to repair their telomeres, potentially granting them longer lifespans. It raises an intriguing question. Could manipulating telomeres hold the key to slowing down the aging process? As we reflect on time's role in aging, we must also consider the groundbreaking scientific discoveries that have reshaped our understanding of time itself. The journey to grasp time's true nature has been a long and fascinating one. It all began with Isaac Newton, whose 17th century work on motion and gravity laid the foundation for classical mechanics. Time in Newton's universe was a constant, a steady flow, unaffected by the motion of objects or observers. For centuries, this view of time as a fixed, unchanging river governed scientific thought. However, everything changed in the early 20th century with Albert Einstein's theories of relativity. His special theory of relativity, introduced in 1905, shattered the notion of absolute time, proposing instead that time is relative. It can stretch and shrink depending on an observer's motion. Then, in 1915, his general theory of relativity revealed that time isn't a separate entity at all, but is interwoven with space, forming the fabric of space-time. This insight radically altered how we perceive reality, showing that massive objects bend space-time, affecting not just the paths of planets, but the very flow of time itself. As we continue to delve into time's mysteries, we are left to ponder, how much of time's elusive nature can we truly understand? Each discovery uncovers more layers of this fundamental force, making it clear that time is far from a simple, unchanging constant. It is instead a dynamic, complex force that governs everything from the tiniest insect to the largest galaxies. Time is the very thread that ties the universe together. But as a dimension affected by gravity and the observer's velocity, another significant breakthrough emerged in the 20th century with the development of quantum mechanics. This was no ordinary discovery. It reshaped our entire understanding of the universe. Quantum mechanics deals with the behavior of particles at the smallest scales, scales so tiny that the classical laws of physics become irrelevant, almost meaningless. In this strange world, time is treated as a backdrop, a fixed parameter, not something that can bend or change. It is this very treatment of time that creates a profound divergence from the principles laid out in relativity, where time is a variable, fluid, and malleable. The collision of these two perspectives has led to one of the greatest scientific mysteries of our time: the quest for a unified theory that can reconcile relativity and quantum mechanics, bringing together the macroscopic and microscopic worlds. The advent of highly precise atomic clocks in the 1950s marked another leap forward in our understanding of time. These extraordinary instruments, which measure time based on the vibrations of atoms, revolutionized our ability to test Einstein's theories with unparalleled precision. Experiments conducted with atomic clocks have not only confirmed the predictions of relativity, but also provided stunning insights into the nature of time itself. For instance, time dilation effects predicted by relativity have been observed firsthand. Time moves at different rates depending on altitude. The closer you are to a massive object, the slower time runs. This phenomenon, which was once an abstract concept, has been verified through experiments that measured time at different altitudes, challenging everything we thought we knew about the flow of time. Then came the groundbreaking discovery of cosmic microwave background radiation in the 1960s, a faint echo from the birth of the universe itself. This radiation, an afterglow of the Big Bang, provides a window into the very early stages of time. It carries within it secrets of the universe's birth and evolution, allowing scientists to trace the origins of time itself. This discovery opened up a new era in cosmology, giving us insight into the age and development of the universe and showing us the moment when time as we know it began. As we approach the end of this journey, we are compelled to ask, what would a world without time look like? A thought-provoking question, one that seems almost paradoxical given that time is so deeply ingrained in the fabric of our existence. If time were absent, what would change? In a world without time, everything would remain static, frozen in place. There would be no growth, no decay, no change of any kind. The most fundamental process, the very act of change itself, would be impossible. Life as we know it would cease to exist. Stars would not be born, nor would they die. Galaxies would remain unchanged, frozen in their current state. The flow of time is what gives motion and evolution to the universe, and without it, the dynamic processes that define life would be inconceivable. From a scientific standpoint, the absence of time would alter the laws of physics fundamentally. Time is woven into the very equations that describe motion, energy, and gravity. Without it, concepts like velocity and acceleration lose all meaning. If there is no passage of time to measure the change in position, velocity becomes irrelevant. In the absence of time, even the fundamental forces of nature would behave differently, and our understanding of reality would be turned upside down. Yet beyond the physical, the absence of time would create an entirely different reality for human experience. Time as we know it shapes everything, from our memories to our anticipation of the future. It is the foundation upon which we build our lives. Without time, there would be no history, no memory, no growth. Our experience of life would lose its rhythm, its progression. There would be no aging, no development, no cause or effect. Concepts like routine, schedules, and even motivation would become meaningless. In a timeless existence, would we still have goals, aspirations, or desires? The absence of time would strip away the very forces that drive human behavior and societal progress. In a world without time, progress itself becomes a distant, irrelevant concept. The mysteries of time beckon further inquiry. In the quest to deepen our understanding, scientists are striving to bridge the gap between the two pillars of modern physics: general relativity and quantum mechanics. General relativity, with its smooth and continuous view of time, stands in stark contrast to quantum mechanics, where time is simply a backdrop to the quantum states of particles. This fundamental clash has led to a theoretical impasse, leaving us on the edge of discovery. The search for quantum gravity, a theory that could unify these two frameworks, is one of the most promising areas of future research. This breakthrough could lead to new insights into time, offering answers to questions we have only begun to ask. Moreover, the study of the early universe holds critical clues. By examining the conditions immediately after the Big Bang, scientists are hoping to unlock the secrets of how time itself came into being. The study of cosmic microwave background radiation, coupled with the detection of gravitational waves, ripples in space-time caused by cataclysmic events, could provide the missing pieces in our puzzle. These phenomena offer glimpses into the universe's earliest moments, shedding light on the nature of time under extreme conditions. Advancements in the precision of time measurement are also playing a crucial role in this pursuit. Atomic clocks, which use atomic vibrations to measure time, have already transformed our understanding of time's flow. With future technological developments, we may unlock even more precise measurements, allowing scientists to test the limits of relativity and quantum mechanics in unprecedented ways. Black holes, with their immense gravity, also present a unique opportunity to study time. These cosmic giants warp space-time so dramatically that they provide natural laboratories to study time's extreme effects. The event horizon, the boundary beyond which nothing can escape, poses deep philosophical and physical questions about time, space, and matter. What happens to time inside a black hole? Does it cease to exist, or does it take on a new form altogether? Additionally, interdisciplinary research involving neuroscience and psychology is shedding light on how we perceive and experience time. This research could eventually lead to a better understanding of the relationship between our brain, consciousness, and the way we experience the passage of time. Finally, advances in cosmology, particularly the study of dark energy and dark matter, are beginning to reveal insights into the future of the universe and the role time will play in its fate. As we study the expansion of the cosmos, we are left to wonder what lies ahead. Will time eventually come to an end, or will it continue on indefinitely, pushing the boundaries of existence? This exploration of time, from the smallest particles to the vast expanse of the universe, offers not only a journey through science, but through the very fabric of existence itself. Time, once viewed as a fixed, unchanging entity, is now understood as a fluid, dynamic force that intertwines with the universe. With each new discovery, we move closer to unlocking its deepest secrets. The journey of time is not just one of discovery, but of profound mystery. An enigma that continues to inspire, challenge, and shape our understanding of the world around us. As we look to the future, we are reminded that time itself is not just a concept to study. It is a mystery to be unraveled, a story yet to be fully told. This journey, much like time, has no end, only the promise of new beginnings and deeper understanding. Thanks for watching, and make sure to subscribe to our channel Starflux for more captivating videos like this.